Hey guys, it's your pal Dave from notesandvolts.com. Welcome to part 7 of the Teensy-Synth tutorial. Today we're going to add pitch bend to the synth so we can do this. So this video is about Midi pitch bend, and in Midi, pitch bend is handled a little differently than other messages. So let's take a look into the inner workings of Midi so we can understand it a little better. Now, one thing you may have noticed is that all the controls in our synth so far have had a range of 0 to 127. And you may have wondered where that number comes from. Why 127? Okay, so let's bring up the Microsoft calculator and set it to programmer mode. This has a helpful feature in that it shows you decimal and binary values side by side. It also shows you hexadecimal and octal, but we don't need to worry about those for now. So if I enter the number 1 in decimal, it will show you what that number is represented as in binary. If you're not familiar with binary counting, let's just slowly increase the value by 1 and you can see the binary digits count up and their decimal equivalent. And there you go. Now at this point you can see I've got 4 bits and the number 15 is my decimal equivalent. So that means in 4 bits I can store the numbers 0 to 15 or 16 unique values. Now if I want to go past 15, I need to add a new bit. So in Midi, a data byte, or the byte that stores the message I want to send, which could be the value of a pot or the velocity of a key press, has to fit in 7 bits. And if you're familiar with computers at all, you probably know a byte contains 8 bits. So why do we only have 7 in Midi? Well, in Midi, the first bit of a data byte is always going to be set to 0. And if the first bit is always set to 0, that leaves us 7 bits for our Midi message. So let's just increase our number. And you'll see as I hit 127, I'm using all 7 bits. So the only way I can go above 127 is to use this 8th bit. And like we just said, I can't. Midi is using that to indicate that this is a data byte. So for most Midi controls, that 0 to 127 range is fine. But what they found for pitch bend is that it's not enough values to represent a smooth curve from one note to another. When I bent up, you'd hear individual steps between the note, which is not how a bend should sound in music. So what they did to get around this is they made pitch bend a unique message in that it contains 2 data bytes. So that basically means we're going to add another 7 bits to give us 14 bits in total. The highest number I can represent with 14 bits is 16,383. And if you notice, here's my bits and I've got 14 ones. And with this number of values, we can smoothly represent the bend from one note to another. Now, if we looked inside this Midi controller, you would see that these controls are actually potentiometers. And when I turn it, the controller is reading the position of the potentiometer and putting out a value of 0 if it's fully counterclockwise, up to 127 if it's fully clockwise. Now, if we took a look at a pitch wheel from a controller, you'd see that there's actually a little potentiometer in there. Probably this exact model. And all they've done is they've put a handle on it to make it easier to turn. But remember, we're dealing with 14 bits now for pitch bend. So at this position, it would give me a value of 0. And at the other end, it would give me a value of 16,383. Now, the one thing to notice is when I release the pitch bend handle, it springs back to the center position. This center position is actually my no bend position. Now, if we kind of pretend that this potentiometer is the potentiometer in here, it makes sense that this middle position is my no bend position. And if I turn it this way, there's a upward bend. And if I turn it this way, I get a downward bend. But I always want to come back to the middle for my natural note or my no bend note. So my 14-bit value for my pitch bend wheel at the low end goes from 0, and at the upper end goes to 16,383. And that means that the middle point between these two values is my no bend position, or where my handle is in the center. And that works out to be 8,192. That's basically how the pitch bend data comes in. 0 to 16,383 with a no bend value of 8,192. The Teensy MIDI library kind of changes those numbers for us to make it a little easier. So what it does is it basically sets this center value as 0 and sets the upper value as a positive number plus 8192 and the pitch bend down value as minus 8191. But just realize that this is the data coming in, but this is the data that the Teensy MIDI library is going to give to us. And we'll see why that helps us in a little bit. So like we've done in the other parts of this project, we're using our pure data control panel to control the parameters for our synth. And you can see I've added this bend controller, and it's labeled as semi, which means semitones. And I've labeled it, or I've got it working so that it goes from 1 to 12 at the high end. So that means I can set my pitch bend range to be 1 semitone to 12 semitones, which, as you know, is an octave. So let's take a look inside of this and we'll see what I did. Once again, this is a very simple control like we've done in the past with all these other ones. And I've set the output to Midi CC 113. Now the only difference is I've added this int object. Now if we look at the properties of this slider, you notice I've set the range. The lower range is 1 and the upper range is 12. One thing I've added is this little object called int. And this is an integer object. So it basically takes the output of the slider and turns it into an integer, which is a number with no decimal point. Now let's see what happens if I get rid of this. Now you notice when I move it, I'm actually getting a floating point number. I'm getting some decimal places, which would just look weird and is not what we want. So this integer object basically gets rid of those decimal places and gives us the output that we're looking for. So all I have to do is connect it between the slider and the number box. And now you can see I'm just getting the integer part, which is giving me the value of 1 to 12. And that's putting that out on CC 113. And that's it for the panel. Pretty simple there. Okay, so let's take a look at the code. And in this project, this is where all the interesting stuff is happening anyways. So the program you want to download is Teensy-Synth Part 7 Pitch Bend Test. And as always, you can download it by following the link in the video description. So first of all, let's take a look at how this program interacts with our control panel. Now, if you remember, we added this new slider called Pitch Bend Semitones. And this lets you set the number of semitones that your pitch bend is going to be able to bend. So we can set it from 1 semitone up to 12. So when I set that, it's going to output that number on Midi controller number 113. And I've added a case in our Midi CC function to accept that number. So if 113 comes in, it's going to, first of all, make sure it's within range between 1 and 12. And if it is, it's going to store it in this variable called bend range. And I've created that variable up in our global variable list right here. Now, the next thing we need to do is actually set our program to listen for Midi pitch bend commands. And if you remember, we do that with these set handle commands. So we've created one before for control change, for note off and note on. So here's the new one I've just created for pitch change. And if you remember, these set handle commands basically tell the Midi library which function I want to call when one of these commands comes in. So when pitch change commands come in, I want to call the function called myPitchBend, which is right here. But before we look at how this function works, we're going to have to do a little bit of theory. Okay, so here's a list of all the notes and their associated frequency in hertz. Now, if you don't know, a hertz is a measurement for the number of cycles per second of a waveform. So if I take this A4 note, it's saying it's 440 hertz. So that means my little waveform is repeating itself 440 times a second. Now, a good thing to know is that if I double that frequency, so if I multiply it by 2 to 880, I will go up an octave. So I will go up to the next A, which is A5 in this case. And also, if I divide that frequency by 2, I will go down 1 octave to A3 in this case. So if you multiply a frequency by 2, you basically go up an octave. If you divide it by 2 or multiply it by 0.5, you go down an octave. Now, another thing to notice is that the distance between notes is not linear. So if you notice down at the low end here, low A is 27.5 hertz and the one semitone up is 29, and then we go to 30, 32. So there's only like 1 or 2 hertz between those notes. Whereas if I look at the top end of the scale, notice there's more than 100 hertz between each note. So that's not linear, that's logarithmic. And that's going to make our math a little more challenging. So what we're going to do is we're going to come up with something called a bend factor. And that's a number we can multiply our frequency by to give us our new frequency. Here's the formula. So it's basically 2 to the exponent of the number of semitones we want to go up or down divided by 12. Let's take a look at that in action. First of all, let's do a simple example, and we're just going to use an octave. So we want to go up 12 semitones. What I do is the number of semitones I want to go up is 12. And we divide that by 12. And I get 1. Now, if I take 2 to the exponent 1, as you may know, I will get 2 out. So basically what we've got here is our bend factor. So if we multiply our original frequency of 440 by 2, I will get 880, which is actually exactly right. That's an octave up. So we've gone up 12 semitones. Now, what if I want to go down 12 semitones? Well, you'll find this function still works. So another way we could think of going down 12 semitones is basically saying we want to go down minus 12 semitones. And if I take minus 12 semitones divided by 12, I will get minus 1. And if, as you may know, if we take a number to a negative exponent, we're actually dividing that number down. So if we go 2 to the exponent of -1, I'm actually getting 0.5, and that's my bend factor. And if I multiply that by my base frequency of 440, I get 220, which is an octave down. So once again, it worked. So let's go back and look at the code now, and hopefully it will make more sense. If you think about it, all we need to do is figure out how many semitones we want to go up or down. So what we really are doing with this piece of code is we're taking our input bend number, which if you remember can be from plus 8,192 to minus 8,191. So we're taking that number in and we're converting that into the number of semitones we actually want to change the note by. So let's just work through an example with some actual numbers. Let's pretend my bend range is set to 1 semitone and that I push the pitch bend control about halfway. So let's say it's outputting a number of 4,000. So the first thing I'm going to do is I'm going to change that input number into a percentage of a semitone. To do that, I'm going to divide that input number by 8,192, which is the full amount it could be. So if I take 4,000 divided by 8,192, that's going to give me approximately 49% of a semitone. Now the next thing we're going to do is we're going to multiply this by our total bend range, which remember can be from 1 semitone to 12, but we said it's going to be 1 in this example. So of course if I multiply this by 1, it's going to give me the exact same answer. This is actually giving me the amount of semitones I'm going up. Once we've got that, we're going to use our formula. We figured out the number of semitones we're going up, which is 0.49, and we're going to plug it into this formula. But if you notice what I've done here is I'm actually going to calculate the exponent part first. So this divided by 12, I'm going to do that here. So I'm going to take this number we came up with and divide it by 12. And that's going to give us the exponent part of our little formula. And here we get 0.04 with all this mess at the end. So let's just put that into memory, and we'll just go 2 to the exponent of that. And that's going to give me a bend factor of 1.028 and so on. So if I multiply that by, say, my base frequency of 440 Hertz, I'm going to get 452 Hertz, which you can see is just a little sharp of 440 Hertz. So as you can see, that's kind of halfway between 440 and 466, which is exactly what I would expect. Okay, so to summarize, basically what this function does, it takes our input bend amount and turns it into the amount of semitones that I'm bending, which I can then plug into this formula and get my bend factor. Now, once I have that bend factor, and here you can see how it's calculated, to do an exponent in Arduino, you use this power function, and this is the base, which is 2, and the bend factor is that thing we calculated up here, the number of semitones. So once I have that answer, I put it into this bend factor variable, which I have created up in the global variable list. And here it is. It's a float variable because it's going to have decimal places. Now, when I actually set the frequency of my oscillators down here in osplay, notice I've added the bend factor. I'm multiplying my base frequency by the bend factor, and I'm doing that for both oscillators. And remember, oscillator 2, we also have a detune factor because we can detune oscillator 2 as well. So there's 2 factors determining the pitch of oscillator 2, whereas oscillator 1 just has the bend factor. Now another thing to notice in this pitch bend function is after I've calculated my bend factor and stored it in the bend factor variable, I'm going to call oscset, which if you remember just resets the frequency of the oscillators without re-triggering the envelope or anything like that. And here it is. All I'm doing is taking the frequency of oscillator 1 and 2 and resetting it with that new bend factor variable. And that's basically going to allow us to hear the change of the oscillator as I move the control. If I didn't have this, you wouldn't hear the change of the pitch until you restarted the note with a new key press. So this allows us to immediately hear the result of our pitch bend. That's a lot of math. Hopefully it wasn't too painful, but if you don't care about any of that, all you need to do is download this program, set your board type to Teensy 3.2, set your USB type to Midi, and upload it to the board. And once it successfully uploads, open up your Pure Data control panel. Remember, go to Media, set your Midi settings to your controller for the input and Teensy Midi for the output. And there you go. Now set your bend range to the amount of semitones you want to be able to bend, and have fun. All right, that's going to do it for this installment. I hope you enjoyed it. Once again, I'd like to thank my patrons on Patreon for helping to make this all possible. So make sure you come back for part 8, and I will see you then.